Hi, in this video we are going to see clique NP-complete problem. Let's see how to prove clique is NP-complete. So before going to see how to prove it, let's see what is clique. A clique is nothing but a subset of vertices from a graph which forms a complete subgraph, right? So let's take this example. Here we are having totally 7 vertices. But this is not a complete graph. A complete graph is nothing but each and every vertices are having edges to all the other vertices. But here C and E are not having edges, and F and D are not having edges, A and E are not having edges. So this is not a complete graph. Now from this graph we are going to see how many complete graphs are there with subset of vertices. Like every single node is forming a clique. That is, size of the clique is 1. In the case if you are taking two cliques, two size clique means here AB is a clique because there is an edge between A to B, BC is a clique, CD is a clique, like that. But DF is not a clique and C and D is not a clique. And G and D is also not a clique. And if you are taking 3 size clique, right? Here ABC is a clique because B is having edges to A and C is also having edges to A and B, and A is also having edges to B and C. So the size of a clique for clique size 3, ABC forms a clique, and similarly BCD forms a clique and EFG forms a clique likewise, right? So but CDF is not forming a clique because there is no edge from D to F. And if you are going for 4 size clique, ABCD forms a 4 size clique as each of the vertices are having connections with having edges with all the other vertices. So similarly, if you are taking B, C, D, E, F, this is not forming a clique. So a clique is nothing but the subgraph induced by Q, which is a graph Q, which is a complete graph. Okay. So let's see how to prove whether this graph is having a clique or not, right? And check whether this problem is NP complete problem or not. So let's take this problem. A given instance is a graph G and a number K, right? So we have to check whether this graph is having a K clique or not, right? So in this example, we can check whether this graph is having 4 cliques, right? That means a clique of size 4, right? And to solve this problem, we have to check whether there is any way to write deterministic algorithm. But as these are having n number of vertices, we have to try each and every n number of vertices. First, let's try with single vertices, 2 vertices, 3 vertices, like that. So surely we cannot solve this in polynomial time. So let's go for non-deterministic algorithm. And in this non-deterministic algorithm also, we are not sure about how to complete it, right? So let's try where if there is any other algorithm, let's try to convert this clique into the form of that and try to reduce it, right? So for that we are going to take the satisfiability problem. As satisfiability problem is NP complete, using that we are trying to prove this clique is also NP complete. Okay, in both the versions we can say if satisfiability Boolean expression is represented in a form of a clique, and if it creates a clique, we can say that this is a NP complete problem. They both are NP complete, right? So let's take the steps here, how to convert this clique into here we are going to take one Boolean expression and convert this Boolean expression into a graph and check whether that forms a clique or not. So if a graph formula is given with clauses C1, C2, Ck, let's take each and every one literals from the clauses, and for each literal x in clause Cj, create a graph vertex, right? So it will be a vertex, right? And put an edge between each of the literal from one class to another class, right? And if these 2 vertices from 2 different classes are complement of each other, and then we should not make create an edge. That means if you are creating an edge, and these 2 endpoints should be true at some point, right? If we cannot assign true, for example, if x and x bar are there, then they cannot be true for true at the same time. So we should not make an edge between 2 complement vertices, right? So that's we are going to choose prove this construction. We are going to draw this graph for the Boolean expression within a polynomial time, and we have to prove that if it creates a K-clique, then you can say this Boolean expression is also satisfiable, and if the Boolean expression is also satisfiable, we can say this clique is also NP complete, right? So let's take a Boolean expression. Here we are having x2 plus x1, x3 bar, x1 bar, x2 bar plus x4, x2 plus x4 bar plus x3, right? Now let's create vertices for each of the classes. So 3 vertices for class 1, 3 green vertices for class 2, and 3 blue vertices for class 3, right? Now we have to draw an edge from each of the vertices in class 1 to all the other vertices in class 2 and class 3, right? x2 to x1 bar is given, x2 to x4 is given, but x2 to x2 bar is not given because they both are complement each other. They cannot be one at the same time. Similarly, we are drawing for edges from x1 to all the other vertices except x1 bar. Similarly for x3 to all the vertices except x3 bar, right? Here the input is x3 bar, right? Here this is x3 bar. So we are not drawing an edge from x3 bar to x3, and we should not draw an edge between literals of the same class, right? So now we have to draw edge from vertices of class 2. So from class 2 already we have done edges for the first class literals. So we have to draw edges for class 2 to class 3 variables only. So x1 bar will be connected with x2, x4 bar and x3. When you are taking x2 bar now from x2 bar we can connect only to x3 and x4 bar. It is not connected to x2. And similarly from x4 we are connecting to x2 and x3, and x4 bar is not connected. Now if you take this x2, x4, x3, this forms a clique, right? So the size of the clique is 3. So we can say G has a clique if and only if satisfiable. That means if the Boolean expression is satisfiable. So when you are taking this G is having a clique, we have to we should have some of the constraint there. Every node for the clique should be from each cluster. All nodes in a clique should be connected. And if you are assigning values 1 for this, each of these literals, then that Boolean variable or this variable will be getting the value 1, and we can say that Boolean formula is satisfiable. It will create the answer true, right? So each literal belongs to exactly one of the K clusters. That is very, very important. And if in a vice versa also we can say if the Boolean function is satisfiable, let A be the satisfying assignment, then we can say select from each class a literal that is true in A to construct a set of subclasses, right? Vertices K and set S. That means the number of vertices should be K, right? Since two literals in A are not from the same class and all of them are simultaneously true, and the corresponding nodes in the graph are connected, and if they form a clique, then you can say this graph has a clique, right? And so this conversion from this expression to this graph, which is creating a clique, this graph is also taking polynomial time, and it is based on number of literals present in all these clauses. So we can say this clique is also a NP complete problem. Thank you.